So besides the few that we want to do together, because we didn't put them on the key, today it's going to be just like the other two review days we had, which is just wide open to whatever you guys want to talk about. So I'll take some specific questions, and then we'll do some of these together that I didn't put on here. But I want to first start with any specific questions or even general questions. You could just say, can you explain to me again the second derivative test, John? Right? I mean, that's fine too, yeah.
I don't know whether this is a good question, but like, so what's like the purpose for Newton's method?
The purpose?
Yeah.
Okay. I love it.
Just like, never mind. I forgot what I was going to say.
Neato. That sounds like something I would start a sentence and I forget the second half of my sentence. Anybody know what's the, I love that question, it's beautiful. What's the purpose of Newton's method?
It like estimates the zeros of the function.
Yeah. That's it.
Okay, cool.
So if I'm given a function, so I could either be, so Newton's method basically finds X intercepts. Blue, let me down, but who's going to work today? Let's see. All right. Newton's method basically finds X intercepts. That question can take on several different forms. So I could just say, I could just give you a function and ask you to find the X intercepts. Or I could say, give you a function, like not a function, but an equation, and say solve this. In which case, what's f of x? No. What is f of x?
X squared minus.
Yeah, x squared minus 3x. Is that the thing I'm trying to get equal to 0, correct? How do I find x intercepts? I make f of x equal to 0. So what's f of x? It must be this, right? Or I could give you solve this equation, in which case, how do I figure out what f of x is? How did we know what f of x was here? Because I had a function that was equal to 0, and how do I solve that? Newton's method finds the x-intercepts, which means solve when it equals 0. Yes? Does that look like this? Gotta make this look like that?
Yeah.
Yeah, and then I can figure out what f of x is. Do you guys, those are the three main types of Newton's method questions. Right? Is everybody semi with me? So the main purpose of Newton's method is to find x-intercepts, which means find when a function equals 0, right? Which means I can solve an equation using Newton's method, because I can just pull one entire side over and I've got an f of x that equals 0, right? You guys, does that make sense? So that's why there's several different kind of questions, but they all come down to make something equal 0, and whatever that something is, that's your f of x. That's what you're going to plug into your Newton's method.
Wait, how did you get ln x equals 3
No. So these are three different examples.
Oh,
They could just give you a function and say, use Newton's method to find the roots. They could give you this, say solve this, in which case this is f of x. Or they could give you this, in which case you'd have to pull one side over, and then you know what f of x is. Now there's kind of a fourth thing, because there's a problem in the homework that says something like use Newton's method to approximate the, where the, I can't remember how it's stated, the absolute max, is that what it was? Yeah, number 36. Use Newton's method to find the absolute maximum value of a function, right? Is everybody with me so far? You guys get this? This is a beautiful thing that you should know. Don't just memorize a procedure or shit. Understand what it's trying to do. If you understand what a method is trying to do, you can identify what problems need you to use that method, right? Now on the test, I'm usually pretty nice. I just say use Newton's method, blah, right? Okay. there is a problem. So there's a problem like this. And it says use Newton's method to find an absolute max. Is this the function that I want to put into Newton's method? If I use this function and I put it into Newton's method, what will it find?
Pi x.
What's Newton's method do?
It finds the zeros.
Finds the zeros. So if you use this function in Newton's method, it will find where this is 0. And I know where this is 0. 0, for example, right? Or any pi over 2 kind of, are you guys, so I don't need help with that, do I? In fact, that's not going to answer this question. How do I find the absolute max of a function? What do I have to find? Derivative, so I can get the, and how do I get critical numbers? Set the derivative equal to, holy shit, so then I'm going to have a function that I want to equal 0. Isn't that what this crazy ass thing does, right? So am I using this function, f of x, f of prime of x, split it in? No, of course not. The question doesn't say, where does that function equal 0, right? So my first step is, I need to figure out what my function is that I'm going to use. And what do I want to set equal to 0? Like you said, the derivative of this. So what's the derivative? Yeah, good. 1 times cosine. And then it'll be x times the derivative of cosine. What's the derivative of cosine?
One negative sine.
Negative sine, like. There's my function, right?
Wait. I thought it would just be 1, no? But why would it be cosine of x minus?
Derivative of x is 1.
Oh,
Leave the
fine.
cosine alone. Right. Okay, I like f prime g. Yes. So that one is a little tricky because the function they give you has nothing to do with the, well, not nothing, but it isn't the function you want to use. You've got to use this guy. So if I were you, I would call this g of x. And then what does Newton's method look like? You guys remember?
F of x.
Now be careful. Right?
Or g.
I like it. G of x n over
G prime.
g prime of x n. Do I have g of x? Yes. Do I have g prime of x n?
Good.
Of g prime of x, I don't have it yet. Right? You guys see what I'm saying? So what's really weird about this problem is you have to take a derivative in the first place just to see what the shit function is. They didn't give it to you. They didn't give it to us like this, this, or this. If I'm doing anything where I do something and then I want to set what I get equal to 0, Newton's method can come into play right then. Yes? Because what does Newton's method do again? It approximates where a function is 0. So what function do I need to equal 0 to find this? The derivative I need to equal 0. But it gets weird because your brain says, I've taken a derivative. You guys see what I'm saying? And this is a weird problem. Haven't we already taken a derivative? Didn't we take a derivative? Yes? But that was just to get what the function is that I need to use here. That's why I would call this g, so that I know I still need another derivative to make this work. I really want this, obviously I want this to make sense. I want everything to make sense. But I can't get Newton's method started until I get the function that I want to equal 0, and that's not this. This. So forget where the shit this came from. That's what I want to put in here. So that is here. The derivative of this is there. And then I can just let my calculator chew that up. Enter, enter, enter. Yes?
So since it's product rule, like you have to put it over g of x, is like what you're trying to say?
Say again?
So since it's like it's product rule and stuff, we have to put it over g of x because
No, I'm sorry. No. Okay. This was the derivative, right?
Yeah.
We talked about that, derivative, I said some other shit, and then I said, I would call this g of x. So then it looks more like, right? Because otherwise you got this going on, and this just feels weird. Because that's the function you're working with, so you need its derivative. So I would say, pretend as if the problem said, here's a function, find out where it equals 0. Right? And then you can start fresh and you can use this, you can use it directly. That's not the function I want to equal 0. That has nothing to do with the question. I need its derivative to equal 0 so I can find the critical. Right? So I'm sorry, I didn't mean to make it look like, yeah. Identify this as g of x, and then this looks more like it's supposed to. Is that all right? So I agree. That problem's a little weird. So I love that. See, you never know. Ask me anything, you have no idea where I'm going to go. But that's one problem that's sort of like that special group of problems. In order to do something, eventually I got to set something equal 0. That's when Newton's method starts to work. So I have to identify what is it I want to equal 0, and that's what I use. Yep.
Horizontal asymptotes of non-rational functions. How would you find them?
Oh. How do I find horizontal asymptotes of anything? What does a horizontal asymptote mean?
X's, right?
Say again?
For X's,
What about the x's?
like where it goes to X. Or
No.
with a vertical.
Where it's undefined.
No, that's vertical asymptote. It's like this. I'm like, is this
It goes like this.
it is so? If this is my horizontal asymptote right there, right? Could I have a function? And let's say I have a vertical here. If I'm doing this, what's going to happen? Eventually, right? Could I have this?
Good.
Yeah. In fact, when could it start to get close to this? Yeah. So again, when does a horizontal asymptote actually come into play? When x gets really freaking big, positive or negative. So if I take the limit as x goes to infinity or negative infinity of the function, the answer is the horizontal asymptote. That's what a horizontal asymptote is. That's why, and watch this. Can I go through a vertical asymptote? Can I have a vertical asymptote and I like go through it? Yeah, exactly. Right? It's a wall. The force field's still up. It's a trap. Right? Pull away. All right? No, that's what I love about it. It's a trap. Okay. No Star Wars people? Fine. I can't cross it because it's where it's undefined. Right? So it can't go through it. What about a horizontal asymptote? Is x big here yet? Are these x's big?
No.
Does the horizontal asymptote come into play yet then? No. So I can have a horizontal asymptote here, and I can go through it an infinite number of times. Infinite number of times. Am I getting closer to it as x gets big? Yeah. Right, so I can cross through a horizontal asymptote an infinite number of times because it just says you got to get close to me when x gets big. And it's saying, I'm getting close. Yeah. Okay. I really want that to make sense. Why can I not go through this? Because it comes from the domain. Domain doesn't handle this shit, so it can't go through it. Why can it go through this? Because it only comes into effect when x gets freaking big. Yeah? Okay. I forgot what the original question was. Did I answer it?
No, yeah,
That was a lot. So it doesn't have to be rational, right? If I asked you, what's the horizontal asymptote of this? Well, as x gets really big positive, this just goes to infinity. But what happens when x gets really big negative? So it's like e to the negative 10, e to the negative 100. It goes to 0. So there's a horizontal asymptote that way. And doesn't that match up with the picture? Yes? Yeah, that's where it comes from, letting x get really big and negative. Okay, good. So rational function is just this process for a rational function led to shortcuts. But this process works no matter what the shift of function is. Okay, I like it. Beautiful question. We focus a little too much on rational functions, and then everybody thinks, well, only rational functions have horizontal. No. Anything else? Yes?
Can you explain inflection points again?
Oh, yeah, okay. What are turning points? Or what's a max and a mid? What happens to the graph at a max or a mid?
It turns.
It turns, which is why it's called a turning point. And tell me, if a graph turns, okay, so if a graph turns, right, so here's a turning point, correct? And there's a turning point. If a graph turns, what is changing about the function in terms of calculus? What's different on this side of it and on this side of it?
Slope.
Slope changes, say more calculus-y. First derivative changes sign. Is that cool? When the first derivative changes sign, that is the location of a turning point, and we call it a local max, or a local min, or extrema in general. You guys, is that cool? Now, you asked me a question. You're being very patient. You're like, I didn't ask about freaking what this shit. Okay, so there's a beautiful analogy though. So this is where f prime equals 0. On one side, what's f prime here?
Positive.
And on the other side, negative. So that would be, if this is A, this would look like this, right?
Yep.
And then, something similar here, call this B. Right? Negative, positive. Those are special points. We call them turning points or axes. Now, second derivative. So what's the second derivative from like here to about here? What's the second derivative in here? What can you tell me about the second derivative here?
Negative.
It's negative, correct? You guys cool? Because it's cupped down. I like it. So it's negative. So you would be unhappy if you held your cup upside down and somebody tried to pour you a drink, right? You would frown. So you would be negative. All right, whatever. You guys get it. And so on this side, it's the f double prime is negative, and on this side, the f double prime is
Positive.
positive. Isn't that analogous to the turning points being where one side is positive slope, other side is negative slope? So this point right about here, one side of it is negative concavity, and the other side is positive concavity. Is that a special turning point in a way? It's where the concavity changes, correct? It's not where it turns, but it's where the second derivative changes. This is cool? So the same way we want to call these things special names because something interesting happens, I want to call this something, and we just decided to call it an inflection point. Does that make? So those critical numbers for first or second derivative are the possible locations of interesting things. What interesting things? First derivative, where the slope changes from positive, negative, or vice versa. Second derivative, where the concavity changes. Positive, negative, negative, positive. So we're going to give those special little names, and we happen to call this one an inflection point. I like it. It's been forever since I actually looked up the word inflect, but it sounds like reflect. But inflect, if you look up inflect, it kind of like means turn. I can't remember exactly what it means. Is that right? Did I go too far? So if I find f double prime of x equals 0 at A, B, and C, are those my inflection points? First off, I would love it if somebody said those aren't points. Right. But are they the location of inflection points?
Positive.
Do you know that? Good, possibly. I don't know. It could be that it stays positive on both sides of A, in which case it's not an inflection point, right? The same way I can have a slope go to 0 and then it's aha. So is that a turning point? Nope. It could trick me. Oh shit. Okay. Maybe. Yes.
A question. So if, let's say you have a critical number where it's undefined, does that count like as a slope change, even though they're not?
Yes, totally. Because can somebody help me out? What's one place where how could a derivative be undefined? What would it look like?
Like a rational function.
Okay, sure. Where I have like now help me out. What's the slope there?
Very positive,
And what's the slope here?
very negative.
Okay, did the slope change? Yes, that's why we still identify on our sign diagram, we still put, but I put a little U there to remind myself something freaky is happening right there.
Yeah, if you asked us for a point there though, there wouldn't be any, right?
Good,
It's like-
exactly.
Okay.
So it's not the location of this is definitely not the location of a max because it doesn't stop somewhere, right? Does that make sense? But it's still where the slope changes. But it's not a maximum because there's no point it gets to. I like it. Now, another way it could be is, there could be a point at A. Does anyone else remember what's another way to not be differentiable at a point? You're gonna be infinite there.
A cusp.
Cusp, there you go. Is that a maximum? Come on, is that a maximum?
Oh, it is.
Isn't it bigger than everything else around it? Shit, yeah, that's a maximum. So it would still have the same, let's see, yeah, I could. Is this plus and this is negative? Yes. For F prime? That's for this one. Wouldn't this one have the exact same? You call this A. Isn't it increasing? Decreasing? And it is undefined at A, yes? But when you plug A in, do you think it's gonna have an output? Of course, yes. Maybe, you guys? I love that question. So if you plug A in and it's undefined, that probably means it goes to infinity there, if the slope is undefined. But it doesn't always have to, right there, right? Would that be an inflection point? How can you tell really quickly from the picture? What's the concavity here? Up. What's the concavity there? Up. I love it. Again, I'm not talking about increasing, decreasing, am I? That's first derivative shit. What's the concavity? Up. What's the concavity? Up. Down would have been like that. This is up concavity. This is up concavity, right? So that would not be an inflection point. Would that be an inflection point? Or an inflection area? Because again, isn't that up? Isn't that up? Okay. Maybe. So there's really good analogies between, I mean, if you look at the practice test, I kind of broke it out so that first derivative, critical numbers for the first derivative, sine diagram. Second derivative, critical numbers for the second derivative, sine diagram. I mean, they're perfectly analogous. It's just what we call what we get depends on which derivative. Is it a turning point, max or min? Is it an inflection point? Depends on which derivative I'm looking at, right? I like it. I like it. Yeah.
Do you ever L'Hopital's rule?
L'Hopital's rule. What about it?
It's like a crash course.
Okay. So I'm not going to go over the derivation again, but let me see. Let me see if I can make something more interesting here. Hold on. Sure, I like it. I like it. Right. So when does L'Hopital's rule, where does it guarantee to work?
0 over 0 or infinity over infinity.
Or any indeterminate form, which I can then put into a ratio. I like it. So that section also talking about other indeterminate forms, right? Can somebody give me one more indeterminate form besides 0 over 0 and infinity over infinity? No? What about this? Believe it or not, that's indeterminate. Because this is a limit, correct? Yes? So if I have the inside going to 1, does everybody agree with me the inside of that's going to 1? You guys see that? Because what's happening to this piece when x gets freaking big?
0.
It goes to 0. And isn't this going to infinity? Isn't that the form 1 to the infinity? Yes? The answer is not 1 though. The answer sure as all hell ain't 1. Because does the inside ever become 1? Does the inside ever become 1? No. So it's really a question about which one is going to where it's going quicker. If this one goes to 1 quicker, then the answer could be 1. If that goes to infinity faster than this goes to 1, then the answer could be infinity, or it could be 2, or it could be e, for example. I really want to, so I love this. This is why L'Hopital's intuitively makes sense. It's all about which one is getting to where it's going faster, right? Maybe? Maybe not. How would I do this problem? Pretty sure this is one that we had to do in the homework just about. How would you actually do this problem? You're all like, I would leave a blank and hope you don't notice. What is the general approach when I have a variable expression raised to a variable expression? It's one of your favorite things that you have to do. Yeah, you gotta log it. I love it. So let me identify. Oh, I gotta do this one. Screw it. We'll do it. Isn't this basically what I'm looking at, right? So the question is, the limit is x to infinity to what? So I can take the natural log of both sides, and this will come down, right? So if I take the natural log of both sides, this comes down. What form is this in now? In fact, let me bring the limit back in. What form is this in? X goes to infinity, so x is going to infinity. And when x goes to infinity, what is natural log of 1 plus 1 over x doing? What's 1 over x doing when x gets big? 1 to 0. So you're left with natural log of 1, which is? 0. Okay. Infinity times 0. That's indeterminate. It all depends on which one's going fast. If this one's going to 0 faster, the answer could be 0. If this is going to infinity faster, the answer could be infinity. If they're sort of going at the same rate, it could be any finite number they kind of agree on. It's a neat idea. Can I use L'Hopital's on this? It's in an indeterminate form, right? What's the one problem with it? It's not in the form of a ratio. Yes? Yes? I really want this. So L'Hopital's works if I have an indeterminate ratio form. That's what it's built on. How do I make that into a ratio?
You could put x on the bottom. Do
Sort of.
X to the power negative 1.
Yeah. Are you guys okay with that? What is 1 divided by a half? 1 divided by half is 1 times 2 is 2. Yeah. So what's 1 divided by 1 over x? Freaking x. Yes? I can do those all day. Right? The old captain are doing captains. Right. Can I use L'Hopital's rule now? What form is this in? The top is 0, right? And what's the bottom do when x gets big?
0.
0. Holy shit! I can do L'Hopital's now. Do you want to do L'Hopital's? No, but you've got to. Do that. I don't know. Are you guys? I mean, I understand this is a lot, but you know it is calculus. but it's a lot, I understand. But again, it's all about almost every time we're supposed to work with something like this, variable, variable. Almost every time I want to take a natural one. Right? Then I look at what I got. Okay, this is indeterminate. Can I factor this? No. Can I do a conjugate? No. I need something else, and I've got L'Hopital's if I can just make it a ratio. All right, so let's see real quick. What's the derivative? What's the derivative of the bottom? Let's start there. L'Hopital's. What's the derivative of the bottom?
-1/x².
I like it. What's the derivative of the top? Well, how does it start off? Your natural log of anything is 1 over that thing times the derivative of the inside, which we already did. Yes? Wouldn't the derivative of the inside be the derivative of 1 over x, because 1 is 0? So I got mine right. Don't these. Look at that shit! Sorry. I'll come in. So this is the limit as x goes to infinity of 1 over 1 plus 1 over x. Which is? We know this from the beginning. When x gets really big, this goes to, yeah, this is freaking 1. Is that the answer? No, because that's the answer to, yeah, so we know the limit of ln y is 1. So if I do e to both sides, I know the limit of y is e. This is actually the most fundamental definition of e, is the limit of this. So this goes to 1 at about the same rate that this goes to infinity. So they both sort of agree on e. Weird. That freaked a lot of us out, so we gave it a special letter because it was freaky. Right? Yeah.
Why isn't that you took like you did 1 over y and the natural log y? Or
Oh, be careful. Are you asking why I didn't take the derivative this time? Is that what you're asking?
I guess I'm just kind of confused. Like, how did you take that form and then like, because you swapped out one of the x's for a y.
No, so the question was here, right?
Yeah.
So then I just said, let me call this y. Right? And let me call it 1. I could call it f of x, I could call it y.
Yeah.
That's a function I want to know the limit of, correct?
Yeah.
But once I called it y, that let me do shit to both sides, yes?
Okay.
So then if I find this limit, I'm going to raise it e to it, so I can kill this natural, and then I'll know the answer for y, which is the original question. Okay. Maybe. Did I do a derivative of this side at any point? Did I do a derivative of this side? Nope. If I did the derivative of this, you understand how that would so desperately suck? Wouldn't that be a quotient rule and all kind of shit? So I didn't. I applied L'Hopital's, which says the limit of some indeterminate ratio is the limit of the derivative of the top over the derivative of the bottom. It's a special method, but I showed you why it works. Okay. People get a little confused. That's why I thought your question was, why didn't I do the derivative of this side? Because I didn't do the derivative of this side. I just applied L'Hopital's. Yeah. All right, let's do this. I want to make sure. I'll take this moment here. I'll give you the answer key. We'll do the few things that I identified that we need to do in class, and then we'll see how much time we got left for more questions. So we got what they want from this here. So the very first thing is the very first problem. Oh, Let me turn this dude on. So this is finding the, I really want this to make sense. So many times in this class we use the word close, right? In a lot of different situations. So this question on number 1, find the interval of x values that make this approximation correct to within 0.01. So the question is, how close do I need my x's to be to -2 in this case, right? In order for the result to be pretty good, within 0.01. So we did this once before, but it is kind of a weird thing. Non-real. I like it. All right. So I want to put in here. So the idea is this. Oh shoot! Let me do a little bit on the board first. Bum bum ba bum. That'll work. Everything's over there. Somebody help me out. What was the function again?
Natural log of x plus 3.
X plus 3. And around a equals -2. And Jeff just. So I did the work. I got the linear approximation. So I got natural log of x plus 1 is approximately x plus 2. X plus 3, sorry. There. Can't read my own writing. That's awesome. Blah, 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 blah. Okay. So I want to know, when is this close to this? How close? Within 0.01. Like it? So what that translates into is, I want this to happen. I really want this to make sense. So this would be, I want the actual answer to be at least what I get minus 0.01, or at most what I get plus 0.01. It'll be within 0.01 then. So then what I want to do is, I want to graph this y1, I want to graph this y2, I want to graph this y3, and just see where they intersect. When does it come into that area, and when does it leave that area? Because again, the idea is, I have some function, I have an approximating, ooh, look at that. Sorry, this is really good for me. And the further I get away from that A, the worse this approximation gets. Do you guys agree with me? If I'm here, how different is it? Pretty freaking different, right? So the question, this question is just, how close do I need to be so that this error is less than 0.01? So visually, it's going to make sense. It's going to be, my approximation is going to be, okay, let's see what happens. So again, the first thing is x plus 2 minus 0.01, right? And then I got my natural log, oh, GF, natural log of x plus 3. And then I got my x plus 2 plus 0.1. Let's see what this looks like. Let's do zoom 6 if you're playing along with me. Where is everything happening, and why does it make sense that that's where everything is happening? Where's everything happening? Around -2, of course, because what happens at -2? What happens at -2?
0.
This is perfectly equal to this. The minute I get a little bit away from -2, my tangent line isn't hugging this anymore. It's a little bit different, right? So I just don't want to let it get so far away that my difference, my error is more than 0.01. That's the idea. So everything's happening right there. So let me use my favorite function in this thing. What is this? This is really good for me. Around -2, of course, because what happens at -2? My tangent line isn't hugging this anymore. It's a little bit different, right? So I just don't want to let it get so far away that my difference, my error is more than 0.01. That's the idea. So everything's happening right there. So let me use my favorite function in this thing. This is the CSI enhanced.
You can do that?
You guys with me? Is that close enough yet? You sure? I don't think so. Let me do zoom box again. No worries. So let's see. Let's get from here to there. All right, I can almost see this. All right. It's going so fast. You're almost going too fast, little computer. All right, so I really want this to make sense. So, still a little bit. Let me zoom one more time for us. Zoom one more time. The important point is, maybe you guys can see this. This red line is the natural log. It's curvy, right? This black line is the plus 0.01, and this blue line is the minus 0.01. So the whole idea is, I want the actual values to be between those two lines. So can you see, like back here, my approximation sucks? It's more than 0.01 off. The minute it touches there, that's where it starts to be good. Then it gets perfect around here, and then it leaves there. I don't know if you guys can see that, so it's still a little bit out. So I just want to find those two intercepts. If I find those two intercepts, I'll know when this starts to be within 0.01 and when it stops being within 0.01. Right? I'll find this. Oh shit, you're facing the wrong. Okay. So how do I find this intersection right here? What do I do? Second, trace, right? And then which one of these? Intercept. So I'm going to go over to where it is. All right. You see right now I'm on the blue line? Right? If I hit enter, now I'm on the red line. Those are the two I want to find the intersection, yes? And then I hit enter, and then I'm already on the guess. Enter. So there's one. So if now real quick, you guys see, -2 is perfect. So how far below -2 can I go? About 0.134, blah, blah, that far below -2, and I'm still within 0.01. It's still pretty good. Good enough for government work, right? And then I do the exact same thing on the other side, right? To find out how far I can get away from -2. Up. I don't know. And again, does this picture make sense as far as, I think this picture should make a ton of sense, right? If I get away from A, then my curve gets further away from my tangent line. And the tangent line is the approximation. So my approximation gets worse and worse the further from A I get. So this question is just saying, how close to A do you have to be so that your approximation is within 0.01? So your approximation is pretty good. Between -2.13 blah blah up to whatever the other one is. Right, you do the same thing, yes.
But for number one, we have to basically use the equation, and then we have to take that, plug it into the calculator.
Yes. So you got your function, you got your floor, and you got your ceiling. And you're just really saying, when does the function get into my house? This time the function comes tunneling in through the floor, and then it exits, right? I'm just sitting there going, what the hell is that? But I want to know, when is it in there? And being in my house means it's approximating pretty well. Maybe. And again, what's right in between the black and the blue? The black line is x plus 2 plus 0.01. The blue line is x plus 2 minus 0.01. So isn't x plus 2 right in the middle? And isn't x plus 2 what we're saying is the approximation? So at this location right here, is the approximation close to the actual value? Not in this case, no, it's more than 0.01 away. So I want this to be close to my, so that's why we found this point. That's when it gets in there. Now my approximation is really pretty good. In fact, it's perfect around here. And then here's where I lose it. Yeah, I really want that to make sense, okay? All right, that's enough of that. Enough.
That's not over y1 over y2.
No. Again, yeah, you gotta. So that's what we got. And then I came in and I said, put this into y1. Put this into y2. Yeah, put this into y2. Yeah. Does that make sense? Okay. All right, I think.
And then you got x plus 2 by doing the linear approximation.
Yes. Yeah. Let's see. Oh yeah. So number 2 is where you have to do the concavity and the inflection points and the maxes and mins, right? And I said we would do this together. So let's take the work I've done. Let's look at that first function. Hopefully it makes sense. Does it make sense the way I try to do this? Right, AB, I try to keep it really clear. Right? So I've got the work done. Let's look at A, f of x, x to the fourth, plus 4x plus 15. Where am I at? 3. So I got my Sine diagram. Look like this. Where are you? Oh yeah, okay. 0, 3, so I got a min at 3, -12. Okay. So I'm just kind of collecting what I've done. Then I got my second derivative sine diagram. It looks like this. So there are inflection points there's 2 of them, correct? Why are there 2 inflection points?
No, up and down.
Yeah, it goes from concave up to concave down to concave up. So it changes around both of these. So 0, 15, right? And 2, -1. Hopefully I plug that in there. I think I did it in my head, which is always exciting. Real quick side note. This is. If I put a 2 in, real quick little stupid side note, but I just want to show you something kind of cool. Do you see how this is 2 times 2 cubed? Is that cool? Minus 4 times 2 cubed. Well, what's 2 cubes minus 4 cubes? 2 somethings minus 4 somethings.
-2.
-2 somethings. Make a plus. Isn't that -2 times 8, -16 plus, I mean, that, it just makes it quicker to do in your head anyway. And of course you're all like, I got this, Jeff. All right. Now, I've got everything I need to graph this thing, because I don't think I asked you. Oh yeah, I did say find the intercepts. Well, the intercepts for this is going to be a little bit difficult. You could find the y-intercept, but can you find the x-intercept of this very easily? Not really. But what's the y-intercept?
17.
Say again? 0, 15. Yeah, we already knew it was being inflection.
I thought it was wrong, and I was like,
No, I couldn't hear
was
you.
so scared.
I couldn't hear you. And I didn't hear a point. I thought I heard a number. So y-intercept 0, 15. And the x-intercepts, you can kind of approximate where they are, but do you see how it's really close to 2? There's an x-intercept close to 2. Isn't that close to 0? That's a little. So if I want to graph this, what kind of scale should I use? What about my x-axis? What are the x values that I need to make sure show up? 3, 0, 2. You guys see that? So that should just be by 1. What about my y-axis?
Oh, by 5s, maybe?
Yeah, something even a little better, maybe. Aren't these both multiples of?
Oh, 3, okay, so
Yeah.
so 3.
Right, but 5 would work. You could approximate it. But I'm going to do 3, 6, 9, 12, 15. And if you guys are as bad as I am with writing and all that shit, probably should bring some graphic. Consider, or I'll give you a graph one. I know they'll do that. So let's plot some stuff. 0, 15 is an inflection point. 3, negative 12, where'd it go? Is a minimum. And 2, negative 1 is an inflection point. I like it. Let's see. Trying to think about. No, all right. One thing you could do. Do you see how it's decreasing here? And it's concave up. So you always kind of want to see how are you starting. I'm decreasing. I'm concave up. Is there a number I could plug in to help me out, to help me get started, sort of? You guys see what I'm saying? So like if I plug negative 1 in, it's going to tell me about where I am, right? So what do you want to put a negative 1 in?
Positive, and then
So you get 1
1 negative, yeah.
minus 4 plus 15. Let me see. Oh, I'm sorry. 1 plus 4, right? Because it's negative 1 cubed. There we go. 1 plus 4 plus 15, I get 20. Yes? So I'm at 20, about right there. And then I'm decreasing concave up, yes? So that gets me started. So I'm going like this. Cup up. And then what happens right there?
It switches.
The inflection point. Is it a max or a min? So I'm still decreasing after that. I'm just now in cup down, yes? So now I want to go like this. And then what happens here? Give myself some more room here. So inflection point. So what happens after that? Cup up. So then I want to go through that. And that would be like the, there's the about 2 that we said. And it looks like there's another intercept over there. But, you know, I would give you, I think I just made this without considering this would be really difficult to get the X intercepts for. You have to do, yeah, this would be gross, right? So on the test, I'll give you something you can actually factor something into the X intercepts. Simple. But it looks like this is roughly in there somewhere. So it looks a little bit like Florida, right? Okay. And then how do you check this?
Lines calculator.
Put it in that area, yeah. So that's the last thing you should do. Because I want this to be rough. I want this to be wrong a little bit, right? If this is too perfect, I really love when people do shit like this. They'll go, it's not even connected because they didn't put their calculator window good enough. I'm like, okay, I appreciate you making it easy for me to tell that you're cheating. Anyway, so be really careful. Do not ever copy the graph from your calculator, ever. If you make a mistake here, I want that on here. And if you can't figure out what mistake you made, leave it alone. Graph it the way that your work's in, right? You guys with this? But I mean, if you graph it in your calculator, it's totally different from this. What's 2 things you should do? If you graph it in your calculator, it's totally different. What's the very first thing you should do? All right, 3 things. So 1 is shed a few tears, maybe. 2 is make sure you plug the damn function in correctly, yes? And if you did plug the function in correctly, then you go back and you check your work, right? And if you don't have time, you leave your graph wrong because you'll lose less points if your graph matches your work. Does that make sense? If your graph doesn't match your work, you're going to lose more points. Yes?
For inflection points, do you just plug in the, like for 0 and 2, plug into the original equation, right?
Yeah, plug that into the original. Anytime I want to know where it is, I got to use the original function. Yeah. Okay. I don't know. So I can come back and do part B, but I want to make sure we do, what was the other thing I did? Oh yeah, we got all the ones on number 8. Let's do number 8 stuff, and then we'll see if we can come back and do that second function from this if you want to. Did anybody, see, be honest, has anybody tried any of number 8 stuff? Oh, good, okay. So let's see what these look like. Number 45 says this. Show 3x plus 2 cosine x plus 5 equals 0. Has exactly one root. What do you guys think? Now listen. Let's say I have a function, and how do I say this? Let's say I know it's increasing and then decreasing. How many roots could it have? I know it's increasing and then I know it's decreasing. It could have 2 roots. And of course it could have no roots, but it could have 2. Right? And that's because I knew it had a turning point. What about a function that never turns? It could only have 1. As long as, so let me ask you this. Does e to the x turn? Does it turn? And what does turn mean? It means slope changes from negative to positive or vice versa. What does e to the x look like? What does it look like? Yeah, help me out. Do it. Anybody? Do it. You can do it. Come on. I love you guys. You're doing this. I don't know. What does that mean? Right? That's all you gotta do. Swoosh. Yes? It's like we're making a shoe company. Here's whoosh. Swoosh. Does it have any intercepts? No. All right. But the only way I could have a function, a continuous function, that has only one real root, it has to always be going up or going down. Does that make sense? Is that enough, though? It also has to be negative outputs and then later positive outputs, right? So if I have a function that is always going up and it starts negative and it's positive later, then it must have one freaking root. Yes? Yes? All right. So let's tackle one of those two. There's 2 things, right? It's got to always be up, going up or down. What does it involve me doing with this function? Taking a derivative. So let's call this f of x. So what's f prime?
3 plus negative minus 2x.
I'm with you. That does. Now think about it for a second. What's the biggest sine can be? 1. So what's the smallest this function can be? Do you understand? Isn't this 3 minus something? How do I make this the smallest it could be? Subtract the most I can. Right? The biggest sine could be as 1, so what's the smallest this function could be? 3 minus 2 times 1? 1. So this function is always greater than or equal to 1. What does that tell me about the function? It is always. What does it tell me about the function? What does it tell me about the slope? It's always positive. What does that tell me about the function? It's always going up. There it is. It's always increasing, right? That's not good enough, though, is it? Because I could have an e function. That's always increasing, but it has no x-intercepts. So what's the second thing I have to show? This function is at least at one point negative, and at some other point positive, right? I like it. So let's look at the function again. Can somebody give me a value that would make this negative? For sure. It's not that hard. This is bounded, yes? So as long as you make this negative, really big negative, then you're golden. Does that make sense? So just make x negative 100. Why not, right? All I need is something. So what is f of negative 100? It doesn't matter. It's less than 0, for sure, right? Now let's do the same thing. I really want you to understand how stupid this is. And again, not stupid like you should understand it, but just, you know, this is perfect. Isn't it negative here at negative 100? It's negative. And what is it at 100? Positive, yes? 300 plus who cares? Plus 5, right? Because this is 2 or negative 2, yes? Is that cool? So at 100, it's up here, and it's always increasing, isn't it? Done. The only way it can have more than one thing is if it turned, and can it turn? No. Because that would mean the slope would become 0 somewhere. You know, it's always at least 1. I know that's weird. But that's how we can use these things that we're learning. We can kind of use them together to do something like this. Okay. 53 gets interesting, I think. Oh yeah, 53 gets funkadelic. Now, let me tell you this. I could do this. I could write up the answers and just send them to you, right? I want to use your time as well as I can. Would you guys rather me go ahead and do these, because then I think we're going to be out of time, or do you have other questions you want to get to and I could just do these and send them to you? What do we think? Any opinion? Do you guys have other questions you want to ask besides these that I didn't get on the answer key? Or you just want to focus on this? Okay, let's do that. Okay. So 53 says, find the smallest possible area of an isosceles triangle that is circumscribed about a circle of Radiosoft. So, right now we're getting into some Illuminati shit. All right. So it's asking you, what is this asking me? It's asking me for the smallest possible area of the triangle. Yes? And it tells me the radius of the circle is r. And it asks me about the area of the triangle. So what do I need to identify about the triangle? What's the area of the triangle? So basically that's what you're asking yourself. If I want you to figure out the area of the triangle, what do I have to tell you? What do I have to tell you?
The dimensions of the triangle.
All right, what are those?
Base.
Base. Okay, what do you want to call this?
B.
Base.
Hmm?
B. For base.
Oh, okay. All right. B is fine. And then what else do I have to know? The height. And what do you want to call that? Holy shit. All right. So then they asked me to maximize this. So far, it's really simple, right? That looks really easy. But the problem again is too many damn variables, right? Okay. Let me make sure, did I forget? The smallest, it's the smallest. So we find the smallest one. Okay. So I want to find the mid. So now what comes into play? All right, this is exceptionally freaky. Any problem we do together, that problem doesn't matter. I keep saying this. What matters is why I did what I did. Is everybody cool with what I did so far? I had to do what I did because they asked me for the area of a triangle, so I need to identify the parts of the triangle that go into the area formula. So that's it.
You identified it by drawing the deadly hollows?
Yes, of course. I didn't get all the parts in there, but yes. Now, definitely.
Sorry.
That's right. Where do I put the R? I can put it anywhere I want to, yes. As long as it goes in the center out, I can put it anywhere I want to, yes. The one place that's going to make the most sense in this problem, all right. what do I want to say here? Well, let's see what you guys do. If I do it like this specifically, I can draw it in like that, right? That's one place I could put it, yes. And I put it so that it made a right angle, because now this triangle here is a right triangle. And isn't that, now this is a different kind of similar triangle. This triangle is similar to this triangle, it's just that this one's been turned around inside. I don't know if you guys see that. So one way you can do similar triangles is to have it like this, and that's the most straightforward way. Yes? Because now this one is just that one blown up, right? And you can see it very easy. Or I could do like that if I draw it correctly. Sort of like what I have here. And then this triangle is this big one turned over and reduced. Maybe. All right, this problem is really fuzzy. All right. So the key here was, I want to relate what I know about the circle to what I don't know about the triangle. Because R, I'm given R. I know R, I know it. I just don't know B and H. So I want to relate these to this. What else? So let me ask you this. What are the dimensions of, what did I call? Oh yeah, okay. I gotta be careful. I called this Y and X, but so now I gotta be careful. What are the dimensions of this triangle? Let's see. So I'm taking this triangle out. What are its dimensions?
1/2.
Yeah, so this would be 1/2 B. Would I call that? I guess, yeah, we could, this is the word. Is that cool? And what's this? This will be interesting. Yeah, this is H. This will eventually be interesting. All right. Now let me take this triangle out. So this triangle is this triangle shrunk down and turned around. So they're still similar triangles. What is this? So again, I took this and I moved it. Right. So what is this? R. And what's this? This is the important part now. This is where it gets a little freaky. And you're all like, this is where it gets freaky? The freakiest thing so far was knowing where to put the R. Yes, would you guys agree? Yeah. But what was this? So let's take a look. This whole thing is H, yes? What is this? So this, I need to know this here, right? So this whole thing is H. What is, let's see, where could I put this? Yeah, this is all different letters than what I did. Oh, yeah. What is, so how long is this then? It's not quite, it's not H. It's H minus R. This here, which is this. I'm sorry, put it in the right place. This here, which is this, there we go. H minus R. Now, sorry, I keep having to go back to my notes because it was X and Y. All right. I can set up a ratio. These would be related, yes? But are these related? Are these identifying the same parts? No. So then, what is this, is the question.
You square H minus R and then subtract R squared.
Yes. So this will be the square root of H minus R squared minus R squared. Holy shit.
Never is bad.
So again, I got this big ass triangle, right? Big ass triangle. I got this part and this part. Do I really care about this part? No. don't care about this part. You guys agree? Do you care about that part? So I have this side and I have this side. Then I have the little triangle that is similar to this one. But I can identify these sides, but again, I don't get it. I don't care about this side. I don't care about this side. I don't care about this side. I need this one. Now I can set up. So let me do this. Now let's leave it like that for now. Now what ratio can I set up? Small, this side to that side, for example. Right? Big side to small side equals big side to small side. Yes. Do you want to solve that? Now again, what's the whole purpose of what we just did? There's what we really want, yes? That's the overriding equation. B and H, too much. I can solve for either B or H. Which one would you rather solve for? I would definitely rather solve for B, because look at H. Screw you, H. How do I solve for B when I just multiply both sides by 2 into R? Now, what can I do? What was the whole purpose of that? And you're all like, you drive me crazy. That's everything you do. Yeah, now I can take this shit, put it there. Now how many variables is area a function of once I put that in there? What? Then I can take the derivative, critical numbers, right? Is it going to be a nice derivative? No. But is it a derivative you can just hammer? Yeah, so this is the hard part. And again, the problem I'm going to give on the test is not going to be this weird, because that's definitely kind of weird to understand. You can do this. You can put the R anywhere you want to. That's the best place to put it. And then to kind of work with the similar triangles correctly, that's a little weird. I understand. Right? But now I've got area equals 1/2 2RH over square root of H minus R squared minus R squared times H. So I just make that H squared. RH squared over the square root of H minus R squared minus R. You can simplify the inside. Now you would do a derivative, which is gross, but you could do it. Set it equal to 0. Oh boy. And then get your answer. All right, quick question. It's 10:15. You guys want to do that now, or you want to go to the next one? Because this, even though this is gross, do you understand how now it's completely recipe? Take this guy's derivative. How would you take this guy's derivative? Quotient rule. I love it. Could you simplify the inside? Of course you could, right? I highly recommend it. Quotient rule, knock it out, set it equal to 0. That looks exciting. Okay. Now, 57 I think is quick. Yeah, 57 should be one, especially compared to the one we just did. 57 says, if this is the velocity of a wave, let me tell you what all this stuff is. A wave of length L and K and C are both positive constants. So L is the only variable there. They tell you K and C are constants, L is the variable, yes? And then they ask you what length causes the wave to be slowest, minimum velocity. So again, what would you do? Take the derivative, yeah. And again, this is, so you can write it like this. 1 over CL plus CL to the -1, right? Is that cool? To the, and now the derivative is easy because that's a constant. It's not prodigal. Well, there is not easy, but it's easier. Okay. Set it equal to 0. Is that all right? Okay, so that one's pretty straightforward because it kind of, we finally got to that point where we take a derivative here after all this shit, and this one starts it. That one's nuts. That one's not too bad. 50. Oh yeah, 58.
Don't laugh at that.
Sorry. And again, these are a little worse than the ones I would actually give you. This one's not terribly bad. Where can I put this? think I'm gonna go ahead and write these up and send it to you anyway, but just because I'm leaving a lot of them undone at the moment. Basically, 58 says you want to construct something cylinder with a dome on top for some reason, and it wants you to minimize. What was it? Yeah, minimize the surface area. Require the least amount of material translates to minimize the surface area. Right? So what do you have to identify? I don't think they gave us anything except the volume. You'll like this. The volume is V. So they tell us the volume is V. Not 20 or 30, but V.
V is for Vendetta.
Sure. Or it's that show with the lizard alien people.
Wait, what?
All right. What do I need to identify about this shape? They didn't tell me anything else, right? So what's true about this shape? It's got, the base has a circle. It's a circle, so it's got a radius. Hopefully you want to call that R.
It's got a height.
What's true about the radius of the dome then? Well, it's obviously got to also be R. And then how tall is the cylinder?
H.
H plus, and then if you add the dome, H plus R.
Screw that. We're going to add the, so here's the idea. The cylinder has a surface area. The bottom has an area. The dome has an area. Here's the neat thing about the area of a sphere. Ready? What's the volume of a sphere? You guys remember? 4/3?
Pi r squared.
Pi r.
Cube.
Volume.
Cube.
What's the derivative of that with respect to r?
4 pi r squared.
Yes. 3 comes down, kills that one, 4 pi r squared. That is the surface area.
Oh,
If I have a sphere and I change the radius by a little bit, doesn't the volume change by the surface area? I always think about it real quick. If I have a sphere and I increase the volume of the sphere by putting a layer of tape on the outside of it, isn't that tape basically equal to the surface area? I really want this to make sense. If I just tape the outside of a sphere, isn't that tape equal to the surface area, right? So how much does the volume increase by? By the surface area. So this is saying the rate of change of the volume is the surface area. If I make my radius a little bit bigger, the volume increases by the surface area. And real quick, here's the area of a circle, yes? What's the derivative of that?
2 pi.
And what's 2 pi r the equation for?
The radius. I mean the circumference.
Circumference, right? Same idea. The rate of change of area is equal to the surface area around that shape. It's crazy. Okay. In this case, it would just be the circumference. So this one, if I gave you a problem like this, I would provide you with surface area formulas. But what's the area of the base? Pi r squared. What's the surface area of a cylinder? You guys remember that? No? Real quick, if I have a cylinder and I chop it, like I cut off a soup can label, and I open it, what shape is it now?
a rectangle? A rectangle.
Rectangle, yes. So this will be the height, right? And what will this be? Right? If I take it and I open it, if I put it back together, isn't this the circle? So wouldn't that be the circumference of the circle? So the surface area of a cylinder is just 2 pi r h. Yes?
What did you get the rectangle from again?
Can you imagine soup can? Cut the label on one side and open it. Isn't that a rectangle?
Yeah.
Take a rectangle and fold it and make a circle on the top. Isn't that a cylinder?
Okay.
I like it. Isn't that freaky? A little freaky. You know, like a cylinder and it becomes a rectangle. What? Plus, what's the surface area of a sphere? 4 pi r squared, right? Is this a whole sphere? This is a hemisphere, so it'll be half of that. All right, so that is what they asked me to figure out. And what do they tell me? They tell me the volume of this whole thing is V. Well, what's the volume? Oh shit, the volume of a cylinder. You guys remember? It's the area of the base times the height, plus the volume of half a sphere would be 2/3. This is why I asked you. Do you want me to do these, or do you want me to focus on another question? All right. So this is what's really beautiful. I want you to tell me something. How many variables are in here? Two. What are they? R and H. How can I use this to help me with this? Solve for R or H. What would you rather solve for? Shit, yeah. Because it's almost by itself already, right? Just subtract that dude, divide by that. And then you can plug that in place of H. And that's going to make it so beautiful. I want you, please differentiate between this. Isn't that going to have a lot of shit going on? Is the derivative really going to be difficult? No. No. It's just going to have a lot of kind of shit thrown around, right? I love you guys so much. So V minus pi r squared, I'm sorry, V minus 2/3 pi r cubed divided by pi r squared is H. Take this, throw it in. I know you guys look at that and you're like, I don't want to. If you do it, you got a lot of writing, but the derivatives are not that difficult. There's a lot of constants and shit thrown around. Okay, so I will write those up and send them out to you, because they're still number 59, but we're overtime, so. Can somebody shoot me an email and remind me to do that? Because I have a lot going on between now and the time that I'll have to do that. If somebody would do that for me, thank you. I'll get that done this afternoon. Miguel's not here. Miguel? Not here? No. Everybody got an answer key, right? Just testing. Okay.